In this screencast, we're going to talk about the physical and chemical properties of enantiomers. So the chemical and physical properties of two enantiomers are identical except for really two things: their interaction with chiral substances and how they interact with plane polarized light. Now, plane polarized light, which is sometimes shortened to polarized light, is light that has an electric vector that oscillates in a single plane. All right. And so plane polarized light arises from passing ordinary light through a polarizer. This is similar to the polarizer like that you would see in sunglasses. Now, a polarimeter is an instrument that allows polarized light to travel through a sample tube containing an organic compound. And it allows for the measurement of the degree to which the organic compound rotates in that plane polarized light. So, for example, if we look here, right, we have a light source, and that's just ordinary light. And ordinary light oscillates in all sorts of directions, right? And that just means it's traveling in all sorts of directions. And so you have a polarizer, and what the polarizer does is it filters out the light that travels in different directions. And so now you have light that travels in the same direction, okay? And what we find is that if you put an achiral sample into the polarizer, the compound does not change the plane of polarized light. Okay, so when we have an achiral compound and it doesn't change the plane of polarized light, we say that's optically inactive. Then, if you look here by contrast, we have the same setup, but now we have a chiral sample. And all of a sudden, the chiral sample will rotate that light, and so it will change the plane of the light. And we say that that is optically active. Right? And you would look through an analyzer and you would see this and measure it. Some newer instruments now will just have a readout that you can use. So we need to go over a few other kind of vocabulary here when we're talking about optical activity. If the rotation is clockwise, the compound is said to be dextrorotary. So this happens if the rotation is clockwise. And then it's labeled as a D or a positive. And then if the rotation is counterclockwise, it's said to be levorotary. And this is either labeled as L or with a negative. Now, two enantiomers rotate in plane polarized light to an equal extent, but opposite directions. So what do I mean by that? Let's say you have an enantiomer A. And you have an enantiomer B, right? If an enantiomer A rotates in plane polarized light plus 5 degrees, then the same concentration of an enantiomer B rotates in plane polarized light to negative 5 degrees. Now, there's no relationship between the R and S prefixes and the positive and negative designations. So you can have a compound that is S and positive, or you can have another compound that's S and negative. And so there's no relationship there. You can only figure this out, whether like the angle of rotation, by doing a measurement. You cannot look at the molecule. Now, we can also have racemic mixtures. Racemic mixtures are when you have an equal amount of two enantiomers, right? Those are called racemic mixtures. They're also known as racemates, right? And a racemic mixture is optically inactive, right? Because what happens is those two enantiomers rotate in plane polarized light to an equal extent, but opposite directions. And so those rotations cancel and no rotations observed. Here's an example of some data. We have enantiomers A and B. Here is A alone and B alone, and then here's a racemic mixture of A and B. And you can see that the melting point of A and B are identical, boiling point is identical. These are going to be equal in magnitude in optical rotation, but opposite signs. And then when you have racemic mixtures, the melting point may be different from A and B. The boiling point may be different from A and B. And what that means is sometimes it's different and sometimes it isn't. And then the optical rotation here is 0. So one of the things that we measure here is specific rotation. And specific rotation is just a standardized physical constant for the amount that a chiral compound rotates in light, okay? Specific rotation is represented by the symbol here, which is a lowercase alpha in brackets, and that equals the observed rotation divided by the length of the sample tube and the concentration of the sample. This is generally at a temperature measured at a temperature of 25 degrees Celsius and a wavelength of 589 nanometers. Now, optical purity or enantiomeric excess, which can be represented also with abbreviation EE, is just a measurement of how much one enantiomer is present in excess of the racemic mixture. Now, you can calculate this by taking the percent of one enantiomer and subtracting the percent of another enantiomer. So, for example, if a mixture contains 75% of one enantiomer and 25% of the other, what's the enantiomeric excess? you would just take 75% and subtract 25%, and that would give you 50% as the EE. And that means there's 50% excess of one enantiomer over the racemic mixture. You can also calculate the enantiomeric excess from the specific rotation of the mixture and of the pure enantiomer. So we can come here and we can say, hey, look, we've got this specific rotation of the mixture. We know the specific rotation of the pure enantiomer. You take this, divide by this, and multiply by 100. And so if you have those measurements, you can also measure it that way. Now, since enantiomers have identical physical properties, they can't be separated by common physical techniques like distillation. Diastereomers and constitutional isomers, though, have different physical properties, and so they can be separated by common techniques. So, for example, if you look here, we've got A and B, and these are enantiomers, but A is a diastereomer of C, and B is a diastereomer of C. And so when we look here, the melting points are the same, the solubilities are the same. So that means that, you can't use differences in solubility in different solvents to separate these using a separatory funnel. You can see here the optical rotation is different, as well as the designations are the exact opposite, right? And this is D because it's positive, and this is L because it's negative. Now, if we look here at C, it's got a different melting point and different solubility. And then we also see where its rotation in plane polarized light is 0, and as well as its designations here. And so it doesn't get a D or L designation. If you have a 1-to-1 mixture of A to B, notice its melting point's different here. Solubility is the same. We see that the optical rotation 0 because they cancel each other out. And then it's sometimes given a designation of D, L. So those are some things that we see there. Now, let's talk about chemical properties of enantiomers for just a second. Two enantiomers have the same chemical properties except for their reaction with chiral non-racemic reagents. And the thing is, most of the things that are in your body, like your proteins, are chiral and non-racemic. And so that means that many drugs are chiral and must and often react with a chiral receptor or a chiral enzyme. And they have to react with that chiral receptor or chiral enzyme to be effective. And so I want you to look at these two examples. This is S-ibuprofen. It's the active component agents in Motrin and Advil. And then this is R, which is a common antidepressant, right? It's the active component in Prozac. And then if we look down here, and we see that one enantiomer of a drug may treat a disease really effectively. So naproxen, for example, is an anti-inflammatory agent. And then if you look at the other enantiomer, though, it's a liver toxin, so it's not as effective. And so a lot of times these drugs need to be either synthesized as one enantiomer or the other, or then separated once they're synthesized, which can be challenging because they have all the same, or most of the same, chemical and physical properties. Another thing that's kind of interesting about enantiomers is the enantiomers in your sense of smell. So look at S-carvone and R-carvone. Research suggests that odor of a particular molecule is determined more by its shape than by the presence of a particular functional group. And so because enantiomers interact with those chiral smell receptors, those enantiomers have different odors. So S-carvone smells like caraway seeds, which you've probably encountered if you've ever eaten sausage, for example. And then R-carvone smells like spearmint. And so they smell different because of the way they interact with our receptors in our nose. So this ends our chapter 5 screencasts. If you have any questions, please feel free to stop by my office.